for the final talk. So Joonghoon is going to talk about quantum testing. So please go ahead. Thank you.
Hi, I'm Joonghoon. Thanks for coming to my talk. Today, I'm going to present our work on statistical quantum program testing. This is a joint work with Kang and advisor Hakjoo at Korea University. First, let me introduce some key concepts in quantum programming. A quantum circuit is the fundamental building block of any quantum program. This diagram shows the implementation of a quantum operator which performs addition on quantum states. In quantum circuit, each wire represents a qubit and each symbol on the wire represents a quantum gate. And each program state is expressed by a state vector. To run the circuit, we need an input state vector. And after we run this circuit with given input state vector, then we also get the output as a state vector. Especially in quantum mechanics, each quantum state is represented as a ket vector. For example, this ket vector expresses the vector in four-dimensional complex space. And bugs can also occur in quantum programming. Even a single misplacement of a quantum gate can induce unintended terms in the output state vector. For example, if we add unintended Z to 0.02 gate into the 4-qubit operator circuit, then it introduces these two unintended terms in the output state vector. So we refer these as bugs, and they violate the intended specification, and in this case, they're the correct addition. So we say that the program state pcat is correct if pcat is the same as the given expected output state ecat. On the other hand, it has a bug if they are not the same. And we can express such incorrect state as a linear combination of expected ecat and unexpected ebotcat with some coefficients as below. So this is the problem definition for our work. The goal is to determine whether the program state matches the expected outcome. First, we need the quantum circuit, the input state, and the expected output state. Then we evaluate the program state pcat, leading to one of two results. In the first case, we detect a bug, which is the unexpected term ebotcat. In another case, we find that the program state is nearly correct with epsilon closeness with statistical confidence. Well, I will explain the reason why I said statistical assurance in a few slides later. Well, in classical programming, checking the program state is quite straightforward. For example, if we want to assert that a variable x is equal to 1, we can find it out by simply reading the data register. In contrast, in quantum programs, there is a limitation that prevents us from directly comparing the qubit registers in the same way. The reason is called Born rule, which is we lose the quantum state as we measure it. After we read the program qubit registers, which is called measurement, then the quantum state immediately collapses into one of their bases, which is if we read the register, then we get ecat or ebotcat only because they are the components of bases. And this measurement procedure is irreversible, which is we lose the exact value of alpha and beta after the measurement. As a result, we can only consider the statistical assurance after the measurement. To test the quantum program with respect to this issue, there is one straightforward way. We can just sample the measurement data from the program state. The whole process of this method is as follows. First, we prepare the program state by running the quantum circuit, and then we measure the program state. If we measure the unexpected state, ebotcat, then we can conclude that the program has a bug. On the other hand, if we measure the expected state ecat, then we should go back to the first step and repeat it until we get the sufficient assurance. Therefore, this naive sampling method requires an excessive number of measurements. To detect a bug, we need even more measurements as the value of B decreases. For instance, in this quantum program, where we introduced a buggy gate to detect the ECAT state, we need an average of 1,000 measurements. Here, measurements refer to the number of times the quantum programs must be executed, which means the circuit must be run for 1,000 times again. In another case, to verify the correctness, we also need a large number of measurements for assurance. For example, to ensure the probability of the unexpected term is smaller than 0.001 in this example, we need about 9,000 measurements, which necessitates running the circuit a substantial number of times. In this work, we addressed this issue by utilizing the amplitude amplification method. Given program state PCAT, we apply the amplitude amplification before the measurement. Then we can increase the probability of measuring the unexpected term, and as a result, we can reduce the number of measurements required to detect a bug, which is eBootCat in this example. Here, one issue arises with this approach. While we can use the Grover iteration for amplifier, which is a well-known amplification operator in quantum computing, to amplify the ECAT state by applying the Grover operator G multiple times, then it doesn't guarantee the amplification without any prior knowledge of the source state. And this is called souffle problem. Instead, to address with this issue, we opt for the fixed point amplitude amplification, which is called FPAA, in our work. FPAA is very effective amplifier for finding the specific number of iterating Grover operation. It guarantees the existence of L star such that L star times of repeating the Grover operation amplifies the probability of measuring eBootCat, which is the bug, with desired assurance. In the verification process, we only need a few measurements because we amplified the probability of detecting the error state, eBootCat, if it exists. Additionally, the program state is also preserved if no bug is present. Therefore, by utilizing FPAA, it requires fewer measurements compared to the naive sampling method, making it more efficient in terms of measurement requirements. In addition, for bug detection, since we amplified the probability of detecting unintended terms, eBootCat, the unexpected state eBootCat can be detected with just a few measurements. For example, if you amplify the probability of measuring eBootCat as 0.95, then we only need 2 measurements are expected to be sufficient. Now we know that the FPAA-based quantum testing is effective in terms of the measurement requirements. For example, in our working example from previous slides, we can reduce the required number of measurements from 1,000 to 2 for bug detection and about 9,000 to 5 for verification. Well, it seems very powerful, but there's one question still remains. Isn't it too expensive? Which is, how about the overhead for utilizing the FPAA? The answer is, in some cases, using the FPAA is more expensive than the naive sampling method. If the probability of detecting eBootCat is high enough, fewer measurements are needed. For example, in this case, where B is 0.05, we could consider simply using naive sampling with 20 measurements, which is quite worthy of consideration. So we need more efficient strategy, which we propose by running multiple FPAAs with a smaller number of Grover operations incrementally. In this study, we refer to this strategy as SFPAA, which sequentially runs FPAA in increasing order. Here, L refers to the repetition, the number of repetition of Grover operation. For example, if we choose such S1 strategy S1, We first run 0 FPAA with 100 measurements, and then 9 FPAA with 3 measurements, and so on. With this incremental FPAA strategy, it requires significantly fewer grover operations, which reduces the overall running cost. For example, using the strategy S1 in the slide before, we need an expected 9 grover operators to detect the first e-boat cat during the repeated measurements. In contrast, directly running the full FPAA requires 34 grover operators. Now I'm going to talk about how to find such strategies in terms of the number of grover operations. Our approach is based on random search with heuristics, but there are 2 additional constraints. While randomly generating the strategy S, not all S are valid for testing the quantum program. First, it must guarantee the bug detection, and second, it must provide the sufficient assurance. And there are a few more conditions, so for more detailed formalization and analysis, please refer to our paper. Since we are testing quantum programs, the best way to evaluate our method would be to run it directly on real quantum hardware and compare the execution times. However, as quantum hardware is still under active development and mature systems are not yet available, we instead compared the total count of executed moments in the circuit for each method. Here, a moment refers to a unit time slice used to synchronize operations when executing on actual hardware. We prepared 3 randomly generated strategies, S1, S2, and S3, for our case study, and compared them to the naive sampling method and to S-naive FPAA, which runs FPAA without a search heuristic. The results show an average verification cost reduction of 58% compared to the naive sampling method. Although S-naive FPAA shows the best reduction rate, which is running FPAA without a random search heuristic, but it presents a challenge for bug detection, and I will explain about this in the next slide. Our method is more effective for bug detection when the probability of detecting an unexpected term, denoted as B, is smaller. When B is 0.001, which is quite small, our search strategy achieves a 40% average cost reduction compared to naive sampling method. Furthermore, our approach significantly mitigates the loss in benefits of using FPAA. In the S-naive FPAA approach that I mentioned at the slide just before, the loss can be as severe as minus 120%, but random search strategy reduces this to just minus 29% on average. This demonstrates a compelling trade-off, making our search strategy a better choice for enhancing FPAA performance. So in this work, we utilized FPAA to test quantum programs. I didn't go into the detailed working of FPAA in this talk, but the core principle is that it transforms the amplitude of the unexpected term from B to some function, PLB. And for more details on FPAA, please refer to the paper. In essence, FPAA operates as an engine that transforms the amplitude, but there may be more optimal quantum circuits and functions for this process. One well-known method to construct a quantum circuit for function f is called quantum singular value transformation, which is called QSVT. So combining these methods could be a promising future direction. To sum up, the problem we addressed in this work is quantum circuit testing. To improve this process, we propose a new scheme for design to enhance efficiency. The core idea of our approach is the introduction of FPAA, with a focus on cost effectiveness. By applying a well-defined FPAA strategy that we proposed, we show that our method is highly effective for testing quantum programs. So this is the end of my presentation. Thank you.
Jens, please.
I have two questions. It was a good talk. In one of the first evaluation slides, your x-axis was going all the way to 500 qubits.
Yeah.
How did you
50
do?
50 qubits, I think.
Could you show again? Maybe I need new glasses, and that's my real question.
Sorry.
Let's get this under control.
I think. You mean this slide?
Not this one. One of the other ones.
This
500
one?
qubits.
Yeah, maximum. Okay.
Huh?
Yeah, that's true. 500 qubits.
How did you do experiments with 500 qubits?
Oh, we did not execute it on some real hardware or.
No, but how did you execute with 500 qubits? What did you do?
Well, the quantum hardware is still in development, and.
No, I understand. What did you do?
Sorry?
How did you get experiments done with 500 qubits? What did you do? There are numbers on the graph. I just want to know. What did you do?
Oh, okay, I see. Sorry. So we counted the depth of the total executed circuit, such as.
So the y-axis is just the depth of the circuit.
Why? Y-axis is the reduction rate. Okay, so we compare.
Reduction in depth. Okay, so
Yeah,
you
reduction
measure in depth.
Yeah, true.
That leads me to my second question.
Okay.
So am I understanding correctly that you're expecting the output to be one out of two states, either the right one or the wrong one, and that's it?
Yeah, that's true.
So what often happens on noisy hardware is that the state you expect will like be very likely, let's say 90%, and then the remaining 10% is distributed over everything else because there's noise in the system. Then your method would be less effective, I guess, if there are many wrong ones.
Yeah, that's true. That's the one of our limitation. And to model the noisy situation, we need to deal with the mixed state, right? But our method does not. Our method only deals with pure state. So I think the reason is FPAA method does not work for mixed state. It is only for pure state. So to deal with some noisy situation with dealing with mixed state, then I think we should consider we should work on the future work for dealing with some mixed state situations.
Okay, very good. I understand. Thank you.
Thank you.
Right. Thank you. I guess if there is last chance to ask OOPSLA 2024 question. So in that case, well, I'm summing that. Thank you very much.
Thank you.
And yeah, thank you.
Thank you.